Okay, this is for the MATLAB script for Newton-Raphson method. So I open the editor. For the Newton-Raphson's method, as we know that in the Newton-Raphson's method we need to have the function and we need to divide it by its derivative. So the implementation is simple. Let's start from the stopping error, say, I don't know, maybe 0.001, because in the Newton-Raphson method normally the method converges very quickly. So even if you put a stopping error of 0.001, for normal functions it will convert very quickly. Okay, and first of all we start from I is equal to 0. We know that it is for the counting of the iterations, and next I want to print the table of first row of the table. So like this: iteration, x values, fx values, and error values. And in the first row of the table, that means for the values, I just want to place the values of the iteration number and the x0 value. X0 value we take as 0, and the function we take as using the function handle or the anonymous function format. Here I am using the same function as exponent of minus x. Okay, and close. We also need the derivative of the function. Okay, so we can say the derivative as f der. Okay, f der, and then we need to manually put the derivative. I mean, MATLAB has no ability to take the derivative for you. So if it is exponent of minus x, it will be minus exponent of minus x. So this we know from the calculus, and for x it's minus 1. So it will be minus exponent x minus 1. So so for the first row, I will input the values of I and x0 only. So x0 is this one, this value. Okay, we will use this function and the derivative values later. So let's check this first. First save it. Newton Raphson lab. Okay, and run this function. So as I can see that it's okay. In the first iteration, that is these, I am starting the iteration from 0, and then starting value is 0, and then these are two empty values, so that we will fill in the second row. Okay, so next we will fill in the second row. So the second row will be calculated with the help of the formula. So the formula for the Newton-Raphson method is xi plus 1. So in this case, I will take I plus 1 as 1 is equal to xi, which is x0, minus the function. So the value of the function at x0. So this will give the value of the function at 0 divided by the value of the derivative of the function, f derivative, at x0, and that completes the formula. So in this case we will with this we will get the first approximation for the root. So since we get the first approximation for the root, we can calculate the approximate error as EA is equal to ABS x1 minus previous one was x0 divided by x1, and yep, okay, times 100. Okay, so this is the percentage error. So now we can print the second values. Okay, this print we can print the second values, f print, and then now I want to print all 4 values. Iteration, which is represented by I, so iteration should change from 0 to 1, so I will put formula I is equal to I plus 1. Okay, so it will be 1. So f print, now it will be I x1 f x1 e a. Okay, so these will be the values. So let's try. So what I get is this. Yeah, so in this case, since I did not put this semicolon over here, so something extra has been printed. So I will put column over here, semicolon over here, and then it will be fine. Clear and CLC, and then what I get is 0, 0.51, and this is that's it. So now I have got the values of the first 2 rows. So the remaining rows I can determine with the while loop. So for while loop, now I think we need to first take the we need to first initialize the value. So now we have x1. Okay, so this x1 value will be now used in the while loop. So I will put while EA is greater than the stopping error. Then I can calculate this value of x, and then the error, and then I can print it. So maybe I need to just copy and paste everything here. Okay, and then rearrange it. Sorry, x1 EA, and then this, and then this. Okay, so let's see whether it makes any sense. So here I am going to have to use the values of x1 for this formula, because the values of x1 should be used. Okay, so I can use the values of x1, and then fx1, and then fx1. I should be using these values, and then I can store it in x1, which will be another x1, but that will make it a little bit confusing. So let's store it in x2, because you see the value of x1 has come from here, from the previous iteration, and then we are using it to find the second iteration, and then from here we have found the value of x2. Okay, x2, and now we are using the values of x2 and x1. We will find the absolute error, so it will be x2 and x1, okay, and then divided by x2. Okay, so it will be the absolute error, and then I increase the counter by 1, and then I print the values x1. No, now here I need to print the value of x2, and then the value corresponding to this x2. So each time x2 will be printed. Okay, and then finally the value of x1 will be updated, because in this when this loop will go back, the value of x1 will be updated. Okay, so we have to update the value of x1. So the value of x1 will be equal to x2. Okay, so that the new value of x2 will be used in the previous case over here, and then I can end it. Hope it makes sense, and then it works well. Okay, so I can now run it, and here it goes. So in this case I can see that the function converged quite quickly, okay, to a value of 0.56714. So here I have only adopted to show only 5 decimal points. So if you want to increase it, then maybe you can increase it to 7 over here, and then we can show some more decimal places over here. So this was the illustration of the Newton-Raphson method, which was quite similar to the previous cases. In each case we have used the while structure for looping, and before looping we have to manually sequentially print out these values, and then I have found this command very convenient, fprintf, and then it gives you the very convenient view of the results.